Welcome back. In this video, we are going to go in more detail about software-defined networking, or SDN. Recall that in the introductory video for this chapter, the network layer can conceptually be divided into two levels, the data plane and the control plane. This allows us to split the network layer functions of forwarding and routing into different devices. The forwarding still happens at the router, but now the routing function can be realized in a general-purpose machine that can manage multiple routers. In addition, this general-purpose machine, called the SDN controller, can also manage Layer 2 devices. In the slide, we see that this logically centralized controller computes the values for the forwarding table and passes them down to the individual routers. But notice that the forwarding table is now called the local flow table. This is an important consideration because the forwarding function can be generalized to more than actions on just the network layer. OpenFlow is the first communication protocol standard in SDN environments. OpenFlow enables the SDN controller to instruct Layer 2 and 3 devices, such as switches and routers, how to handle the incoming data packets. OpenFlow allows these devices from different vendors, often each with their own proprietary interfaces and scripting languages, to be managed remotely using a single open protocol. OpenFlow uses the concept of a flow, which is a specific type of packet defined by the header fields. The SD controller examines the flows, looking at the data packet headers, and determines the actions based upon defined rules that match patterns. These actions then become entries in the local flow tables. A pattern may either specify a pattern for each of these headers or a special wildcard, which indicates a don't care value. For instance, we have seen a bit pattern for IP addresses in a previous topic in this chapter. The bit pattern used as the longest prefix match for forwarding IP packets to output ports. If the forwarding table contains two entries with overlapping entries, which can happen due to use of wildcards, the higher priority rule is used. However, exact match rules, that is, rules that specify the value of all the headers, takes precedence over non-exact match rules. At the bottom of this next slide, we see three examples of action-based matched patterns. Suppose we have a packet with a source address of 1.2.3.4 and a destination address of 3.4.5.6. What will happen to this packet? The action on this packet will be based upon the priority rules defined in the controller. Most likely, in this case, the priority rule would be defined to select the first action, drop the packet. The SD controller can have rules based upon the link layer, network layer, and transport layer headers. The controller can direct the forwarding device to perform different actions, such as forward the packet, drop the packet, or even modify fields in the packet. Notice that the controller also keeps track of statistics. In this slide, we see examples of SDN controller decisions for forwarding packets and firewall actions. The first example shows the forwarding action based upon destination address, the classical router action. The next two examples show firewall rules that block all SSH traffic, port 22, as well as any packets coming from a specific host, 128.119.1.1. This next slide is an example of a rule for an Ethernet switch. This rule tells the switch how to forward Ethernet frames from a specific host interface. The match plus action function unifies different types of devices such as routers, firewalls, Layer 2 switches, and NAT devices. There are even more devices that could be on this list. For example, load balancers. A load balancer is a device that distributes network or application traffic across a number of servers. Note that routers have evolved to execute these match plus action rules, but SDN and OpenFlow allows us to be more generalized and not dependent upon specific vendors. This OpenFlow example slide shows the controller specifying the route for packets originating in one network, destined for another network. There are 3 routers in the diagram, S1, S2, and S3, that are connected in a loop. Hosts H5 and H6 are attached to router S3, and hosts H3 and H4 are attached to router S2. The OpenFlow controller has computed the router's forwarding tables based upon configured rules, and has passed these table entries to the routers. One of these rules determines how the routers direct packets sent by host H5 or H6 to host H3 or H4. The directly connected router S3 forwards these packets out of its port 3 toward router S1. Router S1, receiving its packets on its port 1, matches the addresses and forwards the packets out of its port 4 toward router S2. For these packets which are received on its port 2, router S2 matches the exact destination IP address to direct the packets to the correct host. Note that these rules determine that the router S3 would not send these packets directly to S2. We have completed Chapter 4, which introduced the network layer and its division into the data plane and the control plane. We ended the chapter with the discussion of SDN, where these 2 subdivisions of the network layer are implemented in separate systems. We also studied the internals of routers and looked at the function, elements, and implementation of IP versions 4 and 6. Next week, we will look at the control plane functions in more detail, including a more detailed look at SDN controllers.